Hi there. Welcome to Chapter 2.4 from Stevens' Matrices, Vectors, and 3D Math, a game programming approach with MATLAB. In this chapter, we're going to discuss the cross product. If you recall, in Chapter 2.3, we did the dot product, a fantastic operation, allowed us to do a lot of trig without any trig. The cross product isn't quite as handy, but it has some useful purposes and properties that are certainly worth knowing. So let's get started. I'm going to switch this into full screen mode. So the cross product is defined by this formula right here. And before we go into that formula, it's certainly worth noticing that when you take the cross product, you have a vector cross another vector, and it produces another vector. The dot product produced a number, or what we call a scalar. Right? The cross product actually takes two vectors and returns another vector. This is the first term in that vector. There's the second term in that vector, and there's the third term in that vector. And those terms are all defined in terms of products and differences of the terms in the original vectors u and v, and you take the cross product of those two vectors. Right? And so memorizing it in this form is nearly impossible to do. But if you remember how to take the determinant of a 3x3 matrix, there's a little trick that might help you remember how this formula works. So here's what you do. If you take your vectors u and v and you express them in terms of the standard unit vectors, and this isn't even totally necessary, but express them in terms of the unit vectors I, j, and k, and then create a matrix where the first row, just the standard unit vectors, or the symbols for the standard unit vectors I, j, k, and then in the second row, you put in the elements from vector u, third row, elements from the vector v. And what we're going to do, we'll define the cross product u cross v in terms of this determinant, right? Remember that the single absolute value signs around a matrix represents the determinant. Okay, so here's how we do this. U cross v. If I was going to get the determinant of this 3x3, I would take I times the determinant of this matrix right here, which would be u2 v3 minus u3 v2. So it's I times that determinant that I just talked about. Right? And then we would go across this top row, and you would say, all right, that's j times the determinant, I get rid of that column, of this matrix. And in fact, I made a mistake. It's not j, it's actually negative j, times the determinant of this matrix here, so that's u1 v3 minus u3 v1. So here's the negative j and the determinant of that matrix I just outlined. And then you'd continue across that top row, and you would get to k times the determinant of this matrix, and that would be u1 v2 minus u2 v1. So there's the k, and there's the determinant. And so when you get all done with that, if you put it back into its standard form, you're left with a vector that looks like this. Right? So it's sort of easier to do this cross product when you use the ijk form of the vectors, but that's really just so that you don't have to memorize this formula. Memorizing that formula is fairly brutal. But if you already know how to take a determinant of a 3x3, this is not such a bad way to remember that determinant, or remember that formula. There's some algebraic properties, and I'll go over them fairly quickly because I'm not going to prove them. Maybe I'll say a word or two about it. But I want to get down to the geometric property, because we use the cross product for its one outstanding geometric property that we'll get to in a second. But as I go over these properties, we'll see if I can't reference this formula up here. One of the very important algebraic properties is this first one. U cross V is equal to negative V cross U. So you can't switch the orders unless you throw a negative out in front. And the way that works is if this is U, right, and this is V, then U cross V produces a vector that looks like this. U cross V, and V cross U looks just like that going in the other direction, right? And you can sort of tell by this formula here, using the determinant, if you switched U to the third row and V to the second row, it would switch all these negative minus signs in the opposite direction, and so you get negative V cross U, right? Okay, so we got the first one. Check. Let's see. The cross product distributes across addition, and scalar multiplication does not work like it does in, say, addition. It's more like multiplication, in that if you take the scalar times U cross V, you don't distribute across the cross product. You can multiply U times that scalar, or you can multiply V times that scalar, but don't distribute, don't do both, right? And then U cross 0, that should be pretty clear that that's going to give you the 0. That's a 0 vector, by the way. U cross 0 equals 0 cross U. And basically, if you go back to this formula here, if you make either one of these all zeros, then every time you take a determinant, you're going to get zeros, right? So if you take a cross product with a 0 vector, you get the 0 vector. If you take the cross product of a vector with itself, right, this second to last one, notice I would just have a U, U, U here. Then whenever I took these those cross products again, they would cancel each other out, and again I'd be left with the 0 vector. And finally, one that's definitely a little harder to prove. You just have to sort of expand all your multiplication and addition and show that they're the same. But U dot V cross W is equal to U cross V dot W. You would never guess that. It's just a property, and in fact, I've never really used it, so I'm not even sure how handy it is. Okay, so geometric properties. The biggest one that I want to talk about is this one. The vector U cross V is orthogonal to both vectors U and V. And it goes to this picture here. All right, this vector U cross V is orthogonal to V, it's orthogonal to U, right? Sort of, in fact, it's what they call normal to the entire plane defined by V and U, right? So this is the big one right here. A couple stars by it. Not unlike the dot product, it is related to a trigonometry function. Specifically, if you take the length of U cross V, that's equal to the length of U times the length of V times the sine of the angle between them. And the angle I'm talking about is this angle here between the two vectors. All right. The dot product has a similar relationship, only it's with cosine, and you don't have to take the absolute or the magnitude of the dot product. So the size of the cross product gives you size U size V times the sine of the angle between them. And what this shows us is that the length of that cross product, if you multiply either vector, either U or V, by some scalar C, then that affects the length of the entire cross product. Right? So if you double the size of U, you double the size of U cross V. If you double the size of V, you double the size of U cross V. And it doesn't matter whether you multiply it by 2 or negative 2, because we're just talking about the length here. Okay, U cross V equals 0 only if U and V are essentially parallel, or the same vector going in the same direction or opposite directions, right? Okay, so, and the area, not the area, sorry, the magnitude of U cross V. Let me go back up to here if I can erase just what I need to erase. Otherwise, I'll just erase everything. Okay, so this one was U, and we'll call this one V. Right? If I go here, the magnitude of U cross V is the area of the parallelogram having U and V as adjacent sides. So that parallelogram I'm talking about is this parallelogram right here. Right? So it's that area of that parallelogram. That's if you take the size of U cross V. If you introduce another vector, say W, and suppose W looks like, I'm going to put my V down here. Suppose W looks like this. If I take the absolute value of W dot U cross V, because remember U cross V will be a vector, W is a vector. When I take the dot product, I get a number or a scalar. If I take that absolute value, and it hardly seems like this is worth even knowing, and in fact it might not be, but I'm going to finish it because it's in the book and I'm almost done now, is the volume of the parallelepiped spanned by U, V, and W. In other words, it's this three-dimensional object right here. All right, I'm doing a fairly poor job, but this parallelepiped is this sort of box created from the parallelogram. All right, so we get the area of a parallelogram, or the volume of a parallelepiped, using the cross product. But really, of all of these properties that I've just outlined here, the main one is this first one. U cross V is orthogonal, all right, to both U and V. That's the important one. All right, so when I say, well, let's do an example so you can see how to calculate one of these. Suppose I have this vector U, this vector V. I'm going to find U cross V and V cross U. So I write I, J, and K across the top. And if I'm doing U cross V, as I am here, then this first row is U, second row is V. And so I'm going to take I times the determinant of this matrix, which is this negative 2 minus 0, so negative 2I. And then I'll take negative J times the determinant of this matrix, which is just negative 5, so it's positive 5, but I had a negative out in front, so it's negative 5J, plus K times, let's see, the determinant of this matrix, so that's 0 minus negative 1, so that's 1K. Rewriting that in component form, negative 2, negative 5, 1. Now if I do V cross U, it's a similar process, only I've just taken these two and switched them. Now I have V in the first row and U in the second. That gives me the negative signs that I need. And when I do that, I'm going to first wind up with I times the determinant of this matrix, which is just negative 2, so I get 2I. Then I'm going to get negative J times the determinant of this matrix, so that's negative 5 minus 0, so that's negative 5, so I get positive 5J. And then I go to K, and I multiply that times the determinant of this matrix, which is just negative 1, so I get negative 1K. And when I write that in component form, it's 2, 5, negative 1. When you compare these, U cross V is the opposite of V cross U. And it's worth pointing out, how do I know both of these are orthogonal to both U and V? Well, I can do the dot product. So if this is U cross V, right there, if I dot that with U, and I'll be dotting that vector with U, which is right here, 0, 1, 5. And if I do that dot product, I have negative 2 times 0, which is 0, plus negative 5 times 1, which is negative 5, plus 1 times 5, which is positive 5, which gives me 0. So when I take U cross V and I dot it with U, I get 0. That means these two are orthogonal, or perpendicular. All right? if I do the same thing, only I take the dot product with V, let's see how that plays out. We should get 0 again, right? So take that. What is V? V is -1, 0, -2. -1, 0, -2. I'm going to take that dot product. I have -2 times -1, which is 2, plus -5 times 0, which is 0, plus 1 times -2, which is -2, which gives me 0. So U cross V is also orthogonal to V, because the dot product is 0. And if you can, and now this is V cross U. If you were to dot product that with U, or if you were to dot product it with V, you'd get 0 as well, right? So that's the important thing. U cross V is orthogonal to both U and V, right? And V cross U, likewise, is orthogonal to both as well. Okay, so now that we know that the vector U cross V is orthogonal to both U and V, like that, we've got to figure out which orthogonal it is, because there's one that goes up, one that goes down. And we use what's known as the right-hand rule. And what you do, if you're taking U cross V, you start at U, and you curl the fingers of your right hand, all right? Right hand. You curl your fingers from U to V, and your thumb will be pointed. There's my I'm not brave enough to do a hand, but I'll happily draw a thumb for you. I mean, I guess it would start off with the hand looking like this, and you'd curl your fingers from U to V. Your thumb will be pointing in the direction of U cross V. So if you wanted to find which direction is V cross U going, well, you'd have to take your right hand, only you'd be starting at V and curling your fingers to U. And if you try that a few times, you'll find out the only way you can do that is if you sort of invert your hand and go from V to U, and then your thumb will be pointing down here in that direction. So that's the right-hand rule. It gives you the direction of U cross V. There's a little application in physics, and that used to be sort of the standard application. There's a better one for computer graphics we'll do in a second. But specifically, if you have a vector PQ and you apply some force to the end of it at Q, then the moment of that force about P is given by this thing called the torque vector. And if you take the size of that torque vector, or the moment, the size of that moment, you get what's known as the torque. And basically, it's a measure of the tendency for this vector to go around in the counterclockwise direction. Well, in this case, it's counterclockwise because F is going in this direction. So here's what I mean. So if you take F, now F is originating from here, but if I took F and placed it at the origin, or at P, what you notice is that PQ cross F would go this way, and I'd have a moment vector that's pointing up like that. And the magnitude of that is the torque. And it's certainly worth noticing that if you have a larger vector, or a larger, the way I've thought about this is that you think about this as the torque you get when you apply force to a wrench, and PQ is the wrench. And so, for example, if you double the length of your wrench, you'd also double your torque. And if you double the force, if you push twice as hard, you also double the torque. So either one will give you more torque, either increasing the length of the wrench or pushing harder, using a greater force, I guess. So a somewhat more interesting example, as far as graphics goes, is something called backface culling. And so it's thought about like this: if you have all these objects in your world, in your 3D world, and you have a camera position, maybe this is your camera right here looking out that way, you want to know what objects should you render and which objects should you not render. And one of the methods called backface culling will say something like, well, you render the object, maybe it's a building, if the corners or the vertices of the object lie in a clockwise or counterclockwise, you can choose whichever one, fashion. So you order them A, B, C. And if from the camera's perspective, if they occur, say, counterclockwise like this, maybe then you render them, right? And so these are, from this camera, these vertices appear in a counterclockwise. If you had a camera down here, for example, those vertices would look clockwise, and you wouldn't render them, right? So how do you do this? How do you play this game of backface culling? Here's the thing you have to remember, is that when you take A, B, and you cross, so I'm going to have my 3 points, A, B, C. I want to find out whether or not they occur in the clockwise or counterclockwise position. So I take the vector AB and the vector AC, and I get the cross product, which using the right-hand rule gives me this cross product here, right? And so what it's worth knowing is that if you're up here, right? If you're above this plane, then these points are going to appear counterclockwise, right? Does that make sense? If I'm up here, if my camera is up here, I've got counterclockwise on the orientation of the points. All right, and so what you do is you remember this. So now I put in my point P, and I'll scroll down to the next picture. My point P will be the camera. Suppose that's my camera right there. And there's something worth remembering from chapter 2.3 with regards to the dot product. If you take the dot product of two vectors and that value is positive, then the angle between them is less than 90. If you take the dot product of two vectors and it's less than 0, then the angle between those two vectors is bigger than 90. So suppose this point P is your camera, right? And I have A, B, and C, and this vector AB cross AC. If I take AP, I'm going to look at it down here. If I take AP and dot it with AB cross AC, if that's greater than 0, then this is less than 90, which means I'm above this plane. And if that's the case, what I have is a counterclockwise orientation, right? So I can tell strictly by, taking a dot product and a cross, that's actually a scalar triple product. If it's positive, I know that my points appear in a counterclockwise orientation. If it's negative, then what that means is that if I have this scalar triple product, or AP dot AB cross AC, if that's negative, then this angle here is bigger than 90, which means my P is down here, my camera is down here, and from everything down there, I know that the orientation is clockwise, right? And that's what's summarized right here. We have a counterclockwise orientation. If I take AP, and remember, P is my camera, and if I dot it with AB cross AC, if that's greater than 0, I have counterclockwise, otherwise it's clockwise, right? If you get 0, that means your camera is sitting right on the plane defined by those, and it's going to be a bigger, harder decision as to whether you render it or not. Right? Okay, so that's sort of the application for this particular book, where we're focusing on game programming and graphics. If this was more of a physics type of course, we would use the torque. But let's see. Oh, and our next one, MATLAB. This is we're just going to plot some cross products, right? And basically what I'm generating with this sequence of code, and what you should do is go to the repository and download it and run it. I'm creating these plots, right? There's the vector U, there's V. If you use the right-hand rule, U cross V is going to give you this direction. V cross U is going to give you this direction. And you can play around to make sure that that looks right to you. And basically what I want to introduce here is this function, cross. That's built into MATLAB. Cross UV, when you use it like this, is U cross V. So the first one, order matters, all right? Cross UV is U cross V. And if you have, cross V comma U, that's going to be V cross U. And these two things will be opposite. One will be the negative of the other. And so this little piece of code is called plotting cross products. It's in the Chapter 2 repository, along with that function called vectaro, which is used here to actually draw those vectors so that they're pointing in a specific direction. That way you can sort of get a better perspective of what U and V looks like and what U cross V looks like. And the only other thing in here, so we have the cross, which is a MATLAB built-in function, and vectaro, which is one of the built-in functions from the Chapter 2 repository. Right, and basically what it does is vectaro, you give the original point and the terminal point of a vector and a color, and it will draw an arrow essentially from that point, from the first point to the second point. All right, and as far as MATLAB's concerned, a point, like here's the point 0, 0, so that's the origin, and here's a vector 1, -1, 1. That's still a it's as far as plotting goes, that's still a point, even if you call it a vector, right? So we're going to plot 0 to U, make it red, 0 to V, make it green, and I plot the two cross products. And where do I actually do these? Oh, W1 and W2. All right. So that's what I'm doing. And again, you should just grab this, pull it up, rotate. Feel free to rotate this thing around. Make sure it looks correct, right? What you're looking for is that U cross V should be orthogonal to both vectors and should go in the direction as indicated by the right-hand rule. All right, so that's the cross product. A very practical operation, maybe not as awesome as the dot product, but still very useful for many things. And that wraps up Chapter 2.4. Bye now.